session. It's my honor and pleasure to introduce Professor张益唐. Kronecker once said that God created the integers and all else are work of man. The prime numbers are building blocks of the integers, and the twin prime conjecture is so natural and so beautiful that it must be the conjecture of the God. So, in the following, Professor张益唐is going to talk about his decisive progress towards the twin prime conjecture. You can read this story on the internet, in magazines, in newspapers. So for this story, he needs no introduction. Let's welcome Professor Zhang.
Thank you very much. So let's start with the primes. I'm not going to repeat the so that should be the first time for me to use this. So if I forgot something like this, just mention to me. Okay, let me know. So we start with such a way, assume P is a prime number. And we introduce this, a set, we say it is admissible in such a way. In our notation, we say H is a finite set, like this, where the small h, H1 till H sub k are, first they are distinct, and non-negative images. We say the definition. We say such a set of non-negative images H, capital H, is admissible. That means for any prime P, there is an image with H such that each of these numbers n plus h1, n plus h2, till n plus hk. Sorry, we say that each of these numbers is not divisible by the prime P. That's our definition of the so-called admissible set, capital H. Let's see some examples. We say that H. Actually, this corresponds to the prime, the twin prime conjecture, or maybe something more. We may verify, it's not difficult, that they are admissible. But how about something else? We say maybe some other sets may not be admissible. We say, but let's see this set, 0, 2, 4 is not. Why? We may verify it. I'm not going to give the proofs. Let's try the P equal to 3. Can we find some n such that the n plus 0, n plus 2, n plus 4 are, each of them is not divisible by 3? No. Now I would like to mention a stronger conjecture. That's that should be very important in history, the so-called Hardy-Littlewood conjecture. There are several Hardy-Littlewood conjectures. This is just one. We say that. Conjecture we say if H is admissible, then there should be there exist infinitely many positive integers, let's just say n, such that each of these k numbers, n plus h sub 1 till n plus h sub 2, is a prime. That's a Hardy-Littlewood conjecture. And let's see one special case. We just say, the k equal to 2, and the very simple case, the h is this set 0, 2. That is just the twin primes. Conjecture is the same. But of course, the general statement of the Hardy-Littlewood conjecture is much stronger. Till now, of course, we are far from being able to prove something like this. Let me state my result. But this result currently may not be the best theory. We say assume H is admissible with a constraint which is, we say this depends on the number of the number of integers in this set, which is k. 3.5 million. But now I say this result may not be the best. Or on the website you may find some improvement. But till now, what should be the smallest value for the k? That's it's possible. I don't know. So such a condition. Then there exist infinitely many positive integer n such that the set for each n we say n plus h sub 1, n plus h sub 2. This set contains at least 2 primes. That's my major result. Here, let me say, we say at least 2. But maybe should be at least 3 or at least 4. That should be much harder. Till now, we don't know how to prove it. But we say contains at least 1. That is the trivial. For that, I may not have said something more to say. at least 2. It is significant. So then we say the gaps between the consecutive, and we give a bound something like the 70 million something. Now it is much smaller. I don't know what's the precise value. Now I would like to say, as we know, even we say the subject of number theory is divided into many parts, like analytic number theory, algebraic number theory, and then arithmetic geometry, various. But what I like to say is the analytic number theory has something very special. It may not be too special to me, but maybe we find a lot of problems are reduced into evaluating or estimating a certain sums. So the notation, if we write down the expression, it could be very complicated. But why we can do something like this? We say the treatment of our problem is like this. We introduce something more, is a large number. In our application, we just assume x goes to infinity. And a standard notation for the convention is like this. We say n is similar to x. Maybe we say similar. Just means n is between the x and the 2x. There's something like this. Then we try to introduce a function. I say it is theta. We say theta m. That is just a characteristic function of primes. Thus, we say if it is equal to either 1 or 0, if m is a prime. If m is not a prime, is 0. So we consider the sum, then x is arbitrarily large, it goes to infinity. So we compare. Two sums, which is the so-called S1, it is just equal to, I will introduce something else. The Fn, I didn't mention it, what means that. But I will say, we will come back. Here also, let me introduce something inside. That is J from 0 to K theta. Till now, we have only one constraint on the function f of n. It may depend on x, depend on everything, but only one thing is, I say with must be non-negative condition. Then you say, we may ask, what means that? Then let's compare. That is, let's come to here.
Maybe you should put our other blackboard down.
If with a choice of the non-negative function f of n, we can prove S1 is strictly greater than or S2 is strictly greater than S1. Then let's see here. The summation, this is the same as that. Here we may say it is 1. Here it is that. That's a sum. But for the non-negative f of n, then this implies, we compare these. It's strictly greater than 1. For some n is in this interval. And now x is arbitrary. We just assume for nx sufficiently large, we just consider it goes to infinity. For any large x, always we have some n such that this implies what? I may not say. We say at least 2 primes in this set. This is why also I would like to mention it should be a very general idea in analytic number theory. Reduce a problem like involving the prime numbers distribution to evaluating or estimating and or comparing certain sums. Now the next question. How can we choose? I put it here, only the non-active function f of n. Then we say in a Chinese word it could be like we are seeking a needle under the ocean, right? Because there are too many non-active functions. So let's see. Now we may use this board. Could you hear me? Sometimes I am. I just say how to choose. We have only one constraint. Let's try something like this. Let's try something very simple. So try. We say f of n is always equal to 1. Yeah, this is very simple to also. Then we find that the s of 1 is approximately just equal to x. This is just 1. But this s of 2, by the prime number theory, it is, here we say k is a constant. The major part, here we just say the major part is approximately is equal to this. So of course this choice does not satisfy what we need, right? The S2 is much smaller. And also we may say some other, we may not have enough time to give some other strange choices. And there are some other choices. Oh, let's say, we say f of n is equal to 1 if. But you may say that actually is a very stupid choice. If from here less than, right? Yeah, we say, this choice should work, but we do not know a function like such defined in this way, is it identically equal to 0? It could be identically equal to 0, then that still does not work. Now, I would like to mention something that has this very, very long historical process. Basically, that comes from Selberg. Selberg sieve, the basic one. Then, so which part do we make right? Let's come here. In the history, a lot of problems in the sieve method similar to that. Also, we need to find a function. In general, it should be non-negative. But for some certain n, it should be not very close to 0. It could be equal to 1, larger than 0 or something. Then the Selberg's idea is, first we assume f of n is the square of another real function. We only assume the number n, this is another function that takes the real value. Then the non-negative condition is always correct. Then the question is reduced. What is the number of n? How can we choose this? Here, that could be too long time. I just mentioned something like this. We know the k is the constant here. We already give it. That was the major contribution from Stone, Pins, Udry should be like this. We will say this is GPY. They found a very appropriate choice of the form of the number n. That is, it's very complicated, could be, that we have to write down. That is the summation over the dividers, positive dividers of the capital P of n. I will say something more about that. But we make an restriction. Here we are given a factor which is a number mu d. Maybe too many things. I will explain it. And for normalization, we put an constant factor here. Capital P over E. Then for this logarithm, we have a constant of power. And this equal to this is D is less than capital D. O no, just that's it, just like this. And here, let's see, capital P is a polynomial that takes the product form. Depending on the set H, and here L is an integer, positive integer. It is also a constant. Depending on K, we may choose it flexibly. And the mu D is, I'm not going to repeat the definition, Mobius function. And the capital D is a power of it with the constant exponent of the given larger parameter x, we just say. Here C is a constant. This also comes from the basic idea of Selberg in the sieve method or something like this. We may, but later on I may come back to say something more about this. And we already know it is so complicated, right? Now with such a choice, what should be the results on our sum S1 and S2? That is we say results on S1 and S2. That is S1 approximately equal to a constant, we say it is T1, something like this. X multiplied by the natural log of x with the coefficient is k plus 2l. And S2 approximately equal to another constant. We say T2 star. Also here it is x, the natural log of x. But now we know S2, it itself contains the characteristic function of the primes. So in the evaluation of S2, the arrow term comes to play. That will be the most crucial part. I just say, let me use a standard notation, O of E star. Here, we say the S1 star, S2 star. They are constant. But these constants depends on many things, many other constants. We may say the K, actually it is not only K, the set. This already contains K. We have the K elements in this set, and also another constant L, and then the constant C, maybe something else. And E star, here temporarily, let me just say it equal to the arrow. Where this arrow mainly comes from something later on we may mention. So now the question is, we need to, in order that the S2 is greater than S1, we need the coefficients in the main terms. This is greater than that. Meanwhile, we should be able to efficiently bound this arrow term. If we cannot show this arrow term is small in comparison with the major term, still we are unable to handle it. That's a major problem. Now the results, what? Yeah, we are given with the exponent c, depending on the c value. Then the results could be like this. If c is less than 1/4, then in this situation, the arrow term can be effectively bounded, efficiently bounded, sorry. Is small in comparison with the major term. The order is just, I'm not going to say, by the so-called Bombiri Vinogradov theory. But T2 star is less than T1 star. We are able to evaluate both these two sums. The S1 is simpler, so even I didn't write down the arrow terms here. It should be very simple. But S2, the arrow term is complicated. In order, we are able to handle the arrow term. If we take C is less than the 1/4, we can handle this. We don't worry about this. But now this coefficient is smaller than that. We wish to prove S2 is greater than S1, but we couldn't. Now, on the opposite situation, if C exactly equal to 1/4 is almost the same as this situation, I'm not going to say. Say C is equal to 1/4, that is in my paper, like this. Then, in comparison, if we compare the main terms, the coefficient in S2 star this is larger, but this is smaller. But we need to choose the L, that's a minor problem. Then T2 star is greater than T1 star. So if we just compare the main terms, it's good enough. But till now, one is unable to show that the arrow is small in comparison with the main term. Let me say, we have solved the bounded gaps problem, but still in general, we are unable to show this is small. And to show this arrow term is small, even what I can say is, even we assume some very strong hypotheses, like the generalized Riemann hypothesis, still we are unable to show this. So this is the very deeper problem. Also, we say, as mentioned, we say the gap, the difference is only within the hair breadth, but this is less than 1/4 or greater than, slightly greater than 1/4. But that's a big difference. We are unable to handle the arrow term. Then, what I like to say is, on my paper I say I just give two observations. One thing is like this. say observation, observation 1. We just say in the expression for the number n, we just say, we assume, we impose and constrain, or we just say, we just assume the variable d has only small prime vectors. That is, we say, let me use this p. That's the different from the polynomial capital P. P is equal to, say, equal to the prime of the P, which is less than a very small power of x. Similar like this. Let me rest this part. So in other words, we just assume we redefine the number n is equal to everything the same as that d dividing capital Pn, and that d is less than capital D. And also, we impose an extra constraint. That means for each such a d, the largest prime factor of such a d is less than this power of x. So it is a small power of x, then everything else is the same. And we choose a suitable L. Here I may not have to say something more. We have this one. Then in this way still, oh, yeah, so thank you, I forgot. This is a constant factor. To make it to normalize the form. Still, if we just impose such a constraint, then we just re-evaluating the S1, S2, we get something. Still, if we just consider the major term, the coefficients of the major terms, still is S2 is larger, S1 is smaller. But now, more importantly, we say the observation 2. That's a crucial part. Still like this, we impose and constraint on the coefficients, actually on the d. So we just consider the d. The d has only small prime factors. That is, we say with the constraint D imposed, then the resulting arrow, we say the E star, can be efficiently bounded. Then, still like this, we choose the C equal to the 1/4 plus the reciprocal of 1168, slightly greater than 1/4. Then we impose the constraint here. The resulting arrow can be efficiently bounded. Therefore, we can prove the bounded gaps between primes. Here, what I like to say is that should be a long story. That was the formal works. The work were due to Bombieri, Friedland, and Uranich about the bounding the arrow terms. Was earlier than the Stone Pinch and how to pronounce it, the Yodim maybe. They are concerned to estimate the error in the distribution of primes in certain arithmetic progressions. But they, just like here, we say that D is equal to, capital D is equal to the x raised to 1/4. If we take the capital D's square, it is x to the square root of x. They tried to say, to estimate here we say that also with you, but here this D could be like the D square earlier, but I just put it here. The number, let me say n is similar to x or less than x, that doesn't matter. This is the bounded function. But n is congruent to C mod B. This constraint almost is useless. Here the number, the n, is equal to the Beaumont function. Let me just, essentially it's the natural log of